Welcome everyone. This is another instance of the ML whiteboard. This used to be an internal meeting where we would review papers and best practices on ML ops, ML in general, the latest research that was out there. And we figured it was a great opportunity to not just engage snorkelers, but also our broader community about some of these research topics that we're actively continuing to learn from and build on top of. And so today we're really thrilled to bring aboard Karan Goel, a former lab mate of mine and many others from the Hazy Research Lab, who'll be talking to us about building and adapting malleable ML systems. He's worked on a number of really exciting research papers in this area, and we'll actually cover a whole set of topics here. And so I'll turn it over to Karan, and yeah, thanks so much for coming by today.
Yeah, awesome. Yeah, I'm really excited to give this talk. And yeah, I guess I'll just start then. Hi everyone, I'm Karan. I'm a third year PhD student, almost fourth year at Stanford, doing research in machine learning and systems. And I guess I'm pretty interested in thinking about how to build tools and kind of do research around making machine learning models more robust and easier to use and deploy. So we try to do whatever we can on the academic side, given that we don't necessarily work with customers and kind of boots on the ground, but we do try to think about kind of big picture questions around these areas. So hopefully this talk will walk through some of those ideas that we've been playing around with over the last, I would say, 9-10 months. Okay, so just to set some context, I have a few slides that are a crude attempt at trying to define some level of structure on the various things that people are doing when building machine learning software. It's not necessarily like the only way to define this stack, and it's probably not a way that you've probably seen before, hopefully. But I find it useful from the perspective of doing research on this area to look at things this way. So mainly, I try to split kind of the various kind of ML software things into 4 buckets. First bucket is like program and run. So this is kind of the basic, I would say, set of things that you need to do in machine learning, which is build models and build data sets. And part of this is architecture modeling. Part of this is data programming, which is pretty familiar to the Snorkel audience. And I would say this is stuff that over the last 10 years has really kind of gotten a lot better. So with Torch and Snorkel and all these things, like you can build models, you can build data sets and kind of iterate on those processes much better. Then there's like layer 2, which is once you have a model, you want to be able to measure and monitor that model and understand what that model is doing so that you can improve and repair it. So these 2 layers are very interconnected, but measurement and monitoring is really about trying to understand how the data and the model are changing over time. And what is the model good at? What do we actually know about what the model's learned? Questions like that are what I consider inside measuring and monitoring. And then improvement and repair is about iterative workflows that allow you to take that information that you get from measurement and really act on it. So you want to be able to repair your model, you want to iterate on your data, you want to debias it or change some behavior for your model based on some constraint that might have come up. So that's all of these iterative workflows. And then at the top is this notion of interaction, which is you want to be able to do all of this with some nice interfaces effectively. So you want to allow the human to be a kind of productive participant in this process of building machine learning software. And that could be workflows for subject matter experts, domain experts, or it could be for machine learning engineers, data scientists, and so on. So it's really what do you give them? And there's some exciting things happening in this bucket as well, with things like being able to use natural language to program, and you probably saw demos for this. This slide was actually older than the Codex demo, but I think like with OpenAI's new stuff as well, like there's some pretty interesting kind of widgets that they're building to do kind of programming and other things there. So yeah, there's a lot of fun stuff in each bucket, I would say. But broadly, I think most people would agree that like you can do the bottom bucket pretty well now. You can pretty much get a model and get it going on any task for text and vision that works pretty decently. But it's still harder to do a lot of these things because the structures is still not quite there on what the right way to do things is. So hopefully that was some context. And in this talk, I'm particularly talking about these three buckets and some work that we're doing across them. So it's not going to be as cogent as this bucket might look. So the work is pretty scattered, obviously. We're attacking, kind of narrow problems and trying to figure things out. But this is kind of the larger framing in which we're operating. Okay, so oops, I think I have run into an issue. Sorry, you might see this apply meetup thing because I gave this talk yesterday. So forgive that, but yeah. Okay, so I apparently repeated the slides. Okay, so now we're good. I forgot to remove that. Ignore it. Okay, so for this talk, I'm going to be talking about malleable machine learning systems, which is this idea that you want to modify your system over time to perform bug fixes, hit performance targets, and meet ethical standards. So it's just some set of things, but the idea is that you want the system to be easy to manipulate and improve. What are some of the things that you might want as part of that? Well, some system components might be letting stakeholders interactively measure things. So, understand what's actually happening inside the system, which in this case might mean, what is the model actually doing? What do we know about its performance? Monitoring that model over time, so tracking distribution shift and its effects over time, and then maintaining that model. In some sense, performing these more atomic updates to both the data and the model in order to improve things constantly. So these are some things that I think are, my attempt at building some definition for what might make a system more malleable, right? More, manipulate, more easy to manipulate for a human. And in all of these, a human can do something because there's an interactive aspect. So for measurement, humans can add and remove things or test to understand performance. For maintenance, humans can take or do interventions and take corrective action. And then for monitoring, again, humans can come in and kind of define what needs to get monitored and what actions need to get taken when certain things happen. So that's the idea for malleable systems. And of course, there's a lot of companies that are trying to build things that might look like they're trying to attack parts of this problem. Like somebody's building a monitoring dashboard and then trying to kind of build a company around that. So that's one instance of that. But this is the larger problem again. So I'm going to be talking about these three pieces in this talk. So once again, to reemphasize, measurement is, for the purposes of this talk, understanding fine-grained system capabilities and performance. Monitoring is actually tracking distribution shift and its effects over time. And then maintenance is performing these atomic updates to data and models. So the first piece is measurement. So let's dive into that. So the idea here is that measurement, why it's at in the top figure on the left, and there's sort of these arrows going to the other things, is because you can't really fix things you don't measure, right? And so one simple thing that you might want to do is get more fine-grained model metrics for critical data slices. And so this is probably a familiar notion to most people here, but I think it's a pretty powerful idea, because even if you think about taking an accuracy metric like raw accuracy and then splitting it into even two buckets, right? Like let's say you have a skin cancer classifier and you split that into, dark skin tones and light skin tones. Even with that little bit of information, you can actually do a lot, because you can A, understand if the classifier is biased, and B, it allows you to, or it gives you new ideas on how you can actually fix that. Because maybe you understand now that oh, I had less data for this bucket, so maybe I should collect more data and so on. So this measurement piece is pretty important for all the other things that you might want to do, because it suggests a lot of interesting ideas on interventions that you can actually make. So I'm going to talk about the robustness gym work here, which was kind of an attempt to try to build a single toolkit that does some of these evaluation workflows. And we had other papers that I wouldn't mention, but the second thing here was looking at this notion that sometimes when you're building slices of data, you might want to dig a little bit deeper and look at examples. And so for a particular task, we built some workflows there that let you do more interactive analysis at the example level. So even more fine-grained in some sense. And then the last thing I'll talk about at the end, which is something that we've been building for interactive ML workflows. Okay, so the rest of the stuff is trying to build simple Python tooling to help you do evaluation. That's the basic idea. The kind of backdrop for this work is that we noticed that there are a lot of different ways in which people did evaluation. So there's obviously slicing, but there's also looking at things like sensitivity to perturbations, invariance transformations, or like adversarial attacks, curating some data and just putting it together. So all of these different evaluation strategies that people kind of had in the literature, and what we wanted to do was kind of unify a lot of that and standardize some of the reporting around it. So make it look something more like this thing on the right, where we've put together this report that has a broad summary of different ways in which a model has been evaluated and the result of that. So this was partly motivated by some of the work around model cards and data sheets and all these things, which are trying to make some process or part of the process of doing machine learning more systematic. And so what we hoped was that with this work, we can try to make that evaluation part a little bit more systematic. So that's the general idea. And also, I don't know if you take questions in the middle, but I'm happy to pause at any point if folks have questions. So in summary, this is a Python toolkit for building evaluations and generating these visualizations. And here's kind of the walkthrough of what's going on in this toolkit. It's a very simple walkthrough, so I'll go through it kind of line by line. So first thing that you do with anything is get data and model in. So we have a bunch of connectors to things like Hugging Face to pull in any of their data sets and models and then do kind of analyses on those. And here, the tasks that we support currently are text classification, token classification, and text generation. And we actually have vision and time series now, but less tested. But yeah, we're working on kind of doing this for multimodal data, basically, this type of evaluation workflow, and taking advantage of text there. Okay, so that's the first set of things. And then once you have your data and model, what you want to do typically is run some processing workflows on your data and model. And the idea here is that typically data analysis and error analysis requires access to site information of some kind. And this site information can be pretty much anything, but most often it's metadata that you have lying around about your examples, or it could be things that you generate by tagging your text, so parts of speech tags or tagging entities in text and things like that, or maybe you have predictions and embeddings that come from somewhere. So basically any site information. And what we've done here is give some sort of standard processing workflows as well as some standard abstractions for building those as part of this. And so what that allows you to do is get your data set and then build out your site information so that you can then do analysis on both simultaneously. Okay, so once we have this, the next set of things we want to do is create the evaluations themselves. And here we have this abstraction called the dev bench, which basically is like a giant bucket in which you throw evaluations in, and then you can anytime kind of query it to get a report out. That's the basic idea. So here what we're doing is in a slightly convoluted way, writing a subpopulation for finding which reviews in the IMDb dataset were horror movie reviews. So it's kind of a random function, but here what this function does is essentially take advantage of the site information that we had computed using Spacey. So that would be tokenizing the text, and then try to find if we can intersect the tokens with some list of horror movies. Very simple thing, and then we can return true if we find that there's some intersection between the tokens in our example and this horror movie list, and maybe then we say it's a subpopulation of horror movies. And the reason this subpopulation might be interesting is because prior work found that like horror movies tend to have, at least in reviews, tend to have these weird kind of quirks where people will describe it as very terrifying or something like that, which you wouldn't typically think of as a positive sentiment. But in the case of horror movies, it actually is a strongly positive sentiment. So it's kind of a interesting conflicting evaluation there. So yeah, so here's an example of creating this subpopulation. And then the things that we support here, again, one of the goals for Robustness Gym was to unify all of this. So this dev bench can take in things like subpopulations, transformations of your data, attacks on your data, data that you might have generated, other data sets that you might have, outer distribution data and so on. And then we have a bunch of built-ins, but you can kind of build on top of that. Okay, so once you have the evaluations, then you want to evaluate your model. So the idea is that this dev bench can then ingest your subpopulation, and you can tag it with some identifiable name. And then you can add whatever metrics you care about to this for any model that you might have lying around. And this basically is this exploratory kind of evaluation piece. So allowing you to kind of quickly add new metrics, quickly add new evaluations, and then iterate. And then once you have this added in, you can then immediately kind of just query for a report. And that gives you these robustness reports, which try to summarize all these different type of evaluations into a plot, and is an attempt at kind of doing a little bit of standardization there. And of course, like there's standard things like being able to write these up benches and then reproduce things after you hand them over to someone in order to share results and so on. So hopefully this gives you a general workflow or general sense of the workflow that we built for trying to do error analysis in a kind of iterative fashion in a notebook. So that's the idea here. And this is the robustness report that we get out. So just a few thoughts on this. So here's one that I visualized for BERT based on KSTON, this natural language inference task, which as far as I can tell is only a task that people in research seem to care about. Nobody actually cares about this in the real world. So yeah, but it's an interesting task for a research point of view. So on the right here, what we do is kind of split this into these different evaluation types so that we have this sectioning of like, here's the subpopulation analysis you ran, here's how we did on attacks, here's how we did on transformations of our data, here's how we did on other evaluation sets. So that gives you this kind of structure for the report. On the left, we actually have all the evaluations that we actually ran. So this report was in the paper, and it was an attempt at trying to consolidate what we had seen in the literature in the past couple of years as far as evaluations that people had actually done or had cared about in the literature. So this was kind of our attempt at saying, look, you can take all of these and put them into Robustness Gym and actually implement them and get them into a report. So yeah, so you see a bunch of these on the left. And then at the top, we have all of the metrics. So we have accuracy of 1 here, but obviously you can add any metric that you care about. And just to highlight something here, like this particular report shows that BERT is kind of sensitive to these character perturbations. And so this might be a problem if you're building like a dialogue type of agent that relied on BERT embeddings or something like that. So that's kind of the takeaway here. And there's also other interesting things. You could connect this report to things like, do you actually need tokenization? There's been work that's observed like you're less sensitive to character errors if you actually don't do tokenization work on the raw character directly and things like that. So there's a bunch of interesting implications that you generally get out whenever you see any kind of report here. And the point is that just that we want to consolidate this view and give you a standard reporting template. And of course, like right now, we're still trying to make this even easier, more unified, as I mentioned, for different multimodal applications where you might have both text, images, and other modalities. Okay, so now that we've talked about
Hey, Karan, we have one question from Vashish in the chat. I don't know if Vashish, do you want to just ask it IRL?
Yeah, I mean, the question's in the chat, but basically I was wondering, what kinds of ways can we like slice interesting data when we really don't have like any metadata outside like labels, right? I think you presented like the canonical example of like, bias in like, recognition systems, and like, say you don't have like labels about like, like what ethnicity, like, certain like, faces or something is, if, like, how would you like go about slicing the data? Would it be like more model centric, or is there like something else that we can look at?
Yeah, so one of the things that makes error analysis really hard is that part of it is almost a creative process where, there's not a clear right answer on how you do error analysis because there's not really like one ground truth on what you're trying to discover about your model. So that makes this process pretty tricky. And hard to model and hard to kind of make or hard to get right. But if you don't have labels, for example, then some of the ways that we're at least looking at is this notion that you can compute some site information from your raw example directly. So like the example that I had in the slide where you ran Spacey, right? You're just taking that example and running it through some pipeline that produces information about your example. So maybe it tags pronouns in text, it tags entities in the text. So maybe you can do an entity analysis to find some indication or weak labels about the race and things like that, right? So these are kind of soft signals that you could pick up on the text. And then another set of soft signals comes from embeddings and pre-trained models that you might have lying around. So you can run your text through that and do things like clustering or some sort of analysis on the embeddings to do that. But again, these are not, I would say, settled in terms of like what the right answer is, but just some suggestions.
Okay, great, thanks.
More questions? Okay, so I'm going to move to the next part of the talk, which is monitoring. So far we discussed, how to measure things across, data sets, models in a few different ways, and our attempt at least trying to consolidate some of that into one workflow. And next, now that we have this ability to measure things, what we might want to understand is how do we take that measurement and put it into essentially, a time-bound process where like you're always measuring and you're trying to understand are things degrading over time. And particularly in this case, one challenge that comes up is that you want to calculate metrics on unlabeled data. So the idea here is you took a model, you trained it, and then you have to deploy that model. But once you deploy it and run it on production data or deployment data, there's no labels that you have anymore. So you want to be able to understand, is my model degrading as it's acting on these new examples that are coming in. And so in this bucket, I'll talk about our work on Mandoline. So again, joint work with a few folks in the lab and Kayvon's lab at Stanford. And then, we'll walk through this. Okay, so this is Mandoline. So it's a pretty simple method. And as part of actually working with Charles in the lifecycle team, we've been trying to hook this up to Snorkel flow and the data there. And we've kind of got a notebook that demonstrates that we can actually hook this up. So it's pretty exciting. And I'm interested to see what we can do with this method as part of Snorkel flow. But here's the setup. You have a model, standard machine learning. You train the model on a training set. You validate it on a labeled validation set. And both typically come from some source data distribution P sub S. And the standard assumption in machine learning is that you deploy that model and it's IID, so all your test data will come from P sub S as well. Of course, in practice, that never happens. So you have to think about other scenarios. And in particular, what typically happens is you deploy your model and then distribution shift happens. So you are actually getting samples from a target data distribution P sub T. And one of the things that happens here is that you don't actually have labels. Sorry, nothing seems to be moving. Oh, there we go. You don't actually have labels from P sub T. You just get X's, and then your model, predicts on those X's. And so you want to understand what is my model doing on that data. And in this bucket, we have Mandoline, which is a user-guided framework to evaluate models using slices. And let me walk you through what Mandoline does. So what is a slice? So we just looked at robustness gym and kind of this idea that you want to evaluate using slices. So just to be a little bit more concrete for the Mandoline case, we think of slices here as just user-defined groupings of data. So one example could be negation. So you would say, let me split my data based on whether it contains these keywords or not. So you can also think of them as just slicing functions or things like that, which are probably familiar to Snorkel folks. And similarly, male pronoun, does it contain certain keywords or not? Strong sentiment, does it contain certain keywords or not? So you can define a bunch of these slicing functions. And effectively, what that allows you to do is take your data, all your X's, and compute these slice representations for them. And that gives you kind of a nice summary of your data. So in the example here, we have, I love eating ice cream, and that obviously has no negation, no male pronouns, but it does have this strong sentiment carrying keyword. So the slice that it belongs to is this third one, but it does not belong to the other two. And so you can construct this slice matrix for all your examples in any in-house labeled validation sets that you might have lying around. And of course, you can compute what your model is actually doing on those because you have labels there. And so this gives you kind of some source accuracy, of course, because you can evaluate your model on this, but also this slice representation. And then similarly, what you can do is do the same thing on the deployment data that's coming in. Because again, we're just computing slices and we don't need labels here. We're just computing this matrix representation of our data. And even though the data set is unlabeled, you can still compute this slice representation. And the main idea of Mandoline is comparing these two slice representations to each other. So the idea is we're gonna use our labels from our labeled validation set, but we're gonna consider some examples to be more important in this labeled validation set than others. And we're gonna reweight those examples to find out what our target accuracy is. And the idea is like some examples are obviously gonna look much more similar to the unlabeled test set, while others are actually gonna be things that are not similar at all. So maybe in the test set, we get all negation examples or something, right? Or all the examples come from, or have like male pronouns. So then we don't really care about evaluation on things in our labeled validation set that didn't have those characteristics. So that's the kind of intuition. And the method itself uses importance weighting to do this. So there's, this method, general class of methods around importance weighting for actually calculating metrics on unlabeled data sets. And then we kind of have more stuff in the paper on how we can do this when the slices are noisy and so on. But for the purpose of this, the main idea here is you take this slice representation, you take this slice representation, you take this information about your model and what it got right on the labeled validation set, and you pop out a target accuracy number using Mandoline. So simple. These are the three inputs and the one output that you get out. And this allows you to basically then monitor your data over time. And because I'm covering a lot of ground here, I'll just throw this in that in the paper we showed so we consider like text tasks, image classification, and I think a couple of text tasks and one image classification task, and compared to a bunch of baselines that used importance weighting on raw features as well as on slices. And these are kind of the standard baselines everyone uses. And in many cases, what we found is that we are 5 times more accurate and so on. But like one interesting tidbit there that might be relevant to Snorkel audience is that I think the power of this method comes from having access to that slice information, because a lot of times importance weighting and these approaches that I'm talking about are not very good because they're working on the raw examples to do the reweighting. But here we're using these ones and zeros to figure it out. And that actually makes the process a lot simpler and a lot more effective. So that's the idea here. So the slice representation plus this kind of method is what we did in Mandoline. So that's the Mandoline bucket. Deployment metrics, figuring out what's going on data that's unlabeled. So now that we've talked about these two buckets of measurement monitoring, the next thing I want to touch on quickly is maintenance. So once you understand the measurement and you're monitoring it, can you make fixes to undesirable behavior as part of your model? And here, there are a couple of things we worked on. So one paper is, the paper that I'm not going to talk about is model patching, which is a paper where we tried to use data augmentation and specifically trying to learn augmentations in order to improve model performance. So the idea there very quickly was just, can we generate synthetic data? But instead of generating synthetic data in kind of this fashion where you're kind of taking an image and distorting it, can we compute more semantic transformations where you take an image of a man and turn it into a woman and add more data that way? So that was the idea. And so you can do this for things like skin cancer classification, where you can kind of add more samples to subgroups that might not have enough data by kind of transforming things. Okay, so the thing I'll talk about briefly here is goodwill hunting, which is this paper that kind of used robustness shim to do an analysis of named entity linking systems, and then did this piece of maintenance where we tried to fix one of the systems for a particular use case. So the background here is name entity linking. So I'll just give you a quick brief overview. Yeah. Any other question? All right, I thought I heard something. Yeah, feel free to make me, answer questions at any point. I mean, I keep going, but like, happy to pause anywhere. Okay, so name entity linking is this super interesting task where you have to map strings to things in a knowledge base like Wikipedia. So let's take an example here. So let's say you had a sentence like, when did England last win the Football World Cup? So here, what you would want your named entity linker to do is to take England and map it to the English national football team in order to recognize that that's what England means here, and map Football World Cup to FIFA World Cup, again, to recognize that that's what you probably mean here. So this is a process of disambiguating these mentions inside text. And then typically you use these NEL models as part of downstream systems, such as a question answering system. So in this case, you might actually want to answer this question. So you would take this sentence and then hopefully your question answering system would say 1966. But the critical thing is here is that the NEL part is pretty important, because if you map this England to the wrong thing, then you're going to give the wrong answer. So there's a whole lot of moving components, and they all affect each other. But the main thing is that NELs are pretty important, and they're used in widely in industry as part of most assistants and so on. So a pretty important task. And what we did in this good old hunting work is that we analyzed a bunch of commercial and academic NEL systems off the shelf using robustness Gym. So we had a bunch of interesting findings there. So it was one way to validate that we could analyze relatively complex systems using robustness Gym. And these are like systems like Google, Microsoft's NEL APIs, or like academic systems that people consider to be really good. And the next, so that was part one. And then part two was actually trying to, and that's relevant to this maintenance piece, actually trying to take one of the systems, which was actually built in the lab, and try to guide its behavior for a particular sports question answering application. So the idea concretely was that what we noticed is that this bootleg model had poor performance on these particular use cases that might be relevant to sports applications. So here's another sentence: English player Harry Kane scored a goal in their match against Germany. And what we noticed is that in this case, like bootleg was taking Germany and mapping it to Germany, the country, rather than Germany, the sports team. And this is bad because, again, you don't want your name entity linker to give you the wrong entity out. You want it to give you the sports team type, because then it might be used downstream to answer questions and do other things. And so what we wanted to do was think about simple approaches that rely on doing data engineering in order to fix this. So one quirk of the data we were using, which is Wikipedia, is that it's noisily labeled, it's incompletely labeled, there's not, there's a lot of mistakes and so on. So we did a pretty simple thing, which is we just tried to relabel the training set with a simple heuristic. And again, this should be pretty familiar to folks here, using just a weak labeling function to try to correct some of the mistakes here. And the labeling function we used was pretty simple. Just take this phrase match against and assume that the thing that comes after it, whatever that entity is, should be a sports team, because typically when you have a match against someone, it's against a sports team. So that's the simple, idea that's a sports domain specific idea that you inject into this system, and then relabel your training set using that. And then what we find is that you can basically guide the behavior of the model to prefer actually labeling things as sports team rather than countries. And so, I won't go into super detail here, but what we notice is for the errors that we actually care about, which are these sports related errors for this model, where it's labeling things as countries instead of sports teams, we could get a 25% improvement in performance. So very targeted using just this simple approach. So this is pretty interesting because we kind of took this, end-to-end thing where we took a system, we did kind of error analysis in that whole piece on it. And then we said, we're going to fix a very targeted thing using a single intervention. And we were able to do that. So that's why I think it's interesting to try to think about these end-to-end workflows. And the paper, goes into more detail about what we observed in terms of what happened to the model after we did the fixes. You can look at that. It's at NACL this year. Okay, so that's kind of the the main chunk of my talk as far as looking at things like measurement, monitoring, and maintenance, and the kind of work we've been doing over the past 8 or 9 months in those buckets. Some things that I just threw out here is there's a lot to do in terms of taking things like measurement and going from that to some fix that actually does what you want it to do. So this, I think, is a super interesting area of research, and definitely important to actually getting things to work well in practice. And so some things that are interesting is thinking through what are the ways in which we can actually achieve these fixes. And a lot of them are these data-centric things that you do, which is do data augmentation, collect more data, actively sample more data, weekly label more data, change how you process your data, and so on. So I'm pretty interested in thinking about how you can systematically do fixes using some of these approaches. And then, of course, there's also model-centric approaches like changing how you're actually doing training. Maybe you do multitask learning instead of single task learning. Maybe you do meta learning. You change the training algorithm instead of doing empirical risk minimization. Maybe you do like some sort of group robustness type of approach or something like that, distribution robust optimization, and so on. So there's a lot of different buckets of fixes that you can apply and mix and match. And then they obviously have a ton of trade-offs in terms of how fast they are, how targeted they are, how what side effects they might have. And so the study of this is something that I'm very interested in more broadly. And then, of course, like I wish we had things like atomic fixes to models, so you can kind of iterate on a model like you do on software, so that you can push model 1 and model 1.1, and you really understand exactly what you changed about the model. And it's not something that we do a very good job at yet. But yeah, broadly pretty interested in understanding these trade-offs of methods. Last thing I'll talk about super quickly is this new project that we started a couple of months ago, 3 months ago, called Meerkat. And this project is trying to do sort of this building for a data substrate that might live underneath some of these workflows for measurement, monitoring, maintenance, and so on. And the idea is like, especially for, I think it was motivated especially by error analysis, where you want to be able to use all that site information. You want to be able to analyze embeddings and all of these other things, and you want to be able to do it in your notebook or in an interactive environment, so that you can understand and immediately get feedback on what you're analyzing. So it's a very data analysis type thing. And from our perspective, it felt like pandas wasn't enough, because it's kind of centered more on data analysis for time series tabular data, while modern machine learning has a lot of other things that just require more machinery, basically. And so, quick example with what you can do in Meerkat. You can load in, some data that you might have in a CSV into a data panel, which is very much like, you can think of it as a data frame because that's the closest analog. And underneath the hood, what we do with Meerkat is we support a bunch of backends. So your data can be represented in pandas. It might be represented as torch tensors, NumPy arrays, arrow tables, things like that. And then you have all this data you can load in, and then you can compute these specialized, typed columns, like an image column from file paths. And then the image column kind of has things that are image-like, so you can look at the images and so on. You can do image operations on them. You can do torch transforms on them and stuff like that, and construct data loaders from them. And then we also have these, other columns. Again, once you type columns, you can construct most of the important types that you might want in machine learning. So things like prediction columns that understand, things inside them are logits or probabilities. And so, you can do kind of specific operations for those, or embedding columns, which I think are the most interesting, so that you can actually execute embedding workflows. So doing things like projecting the embeddings down, or maybe doing interesting joins between data panels using embeddings, all things that you're thinking about and working on. But overall, this provides a data structure where you can kind of house all this different data and not have it kind of splayed around in different, one torch tensor here and like one pandas data frame there and so on. And that generally should make error analysis and stuff easier. And one of the things we did was we built this and then we hooked it back into Robustness Gym and changed out that data backend. So now Robustness Gym and all those error analysis workflows that I talked about run on top of these data panels. So you can load any data type in and then do error analysis on top of that. And we're still kind of building those kind of validating use cases for image data and for time series data and all these other data types that are interesting. But that's something that should be possible to do soon. And yeah, just error analysis on top. But yeah, if you're interested, definitely use this and give us feedback. It's just a tip install, and then hopefully a drop-in for a lot of things you do. Well, not necessarily. Like if you're somebody who's a Power Pandas user, you might hate Meerkat because a lot of what we did was remove some stuff from Pandas that we didn't like. So you know, but definitely try it and give us feedback. Okay, so I'm just gonna stop here. Here's some of the work that I talked through and couldn't talk through because of time that you can look at. Most of it is from this year, so pretty current in terms of our interests. And then we also have this, GitHub for data-centric AI, which is, something that we're pretty interested in. And of course, Snorkel is pretty interested in as well. And definitely check that out and advertise it if you can, and add to it, whatever. Like there's these awesome lists that I really want to grow. And if you have ideas and you have time, definitely contribute. Even one link is good, But yeah, that's my talk. Thanks so much for listening. Let me stop sharing my screen. Or maybe I should keep sharing.
Well, I know we're at a time, so no pressure if folks have to hop. But thank you again, Karan. This was an amazing summary of some of the great work that we're doing. I'm sure we have a bunch of follow-up questions. I mean, I have a ton myself on some of the specific works that you've done. But yeah, I mean, if anyone has any last questions or can stay for a few minutes, that was a great time.
I've got one, if that's okay.
Yeah.
Are we okay? Cool.
Yeah.
So first of all, of course, great presentation. And as you know, we're big fans of all of your data-centric work. I had a question specifically about slices and the way that they're defined, since a lot of your work, takes a look at that finer grained understanding of what's going on beyond a single metric.
Yeah.
So there obviously are ways of custom defining slices, and you showed some examples of that. There are also various sort of automated or standard ones, like what you might see in the benchmarks that look at various linguistic properties or things that have been deemed trackworthy. In your experience, is there what's the value in some of the standardized ones versus the custom ones, and where do you see people finding the most insights or the right sort of ROI, I guess, on effort to define a slice versus use a standard one, and then what that tells them about their problem?
Yeah, it's a really good question, and basically this is the main question that I grapple with every week, more or less, which is what's the trade-off between cheaply and generally defining these slices versus spending a lot of effort in curating slices that we understand are really good. So for example, there's the work on stratification where they you looked at pneumothorax and they found one slice, right? That was really important, where the idea there was you have these chest x-rays, and then they noticed that some of the models systematically underperform on some slices of data. And that took a lot of effort to understand, but obviously has a lot of value for that particular domain, but is inapplicable to any other domain, obviously. I think for text specifically, there seem to be these general ways of analyzing text that I suspect yield good slices. So definitely what I've seen across things like, I would say, dialogue, question answering, summarization, and name entity linking, are that the patterns for how you define slices are fairly similar, because you're looking at parts of speech or just analyzing the entities and what's being said in the text, right, effectively. And even crude pipelines can get to a lot in that bucket. I think what's harder is to understand if the slice degradation is because it's correlated with some other slice that's actually the reason why that slice that you were saying is poor, or if it's the sort of causal thing of if I was to take an example and remove something from it, would that degrade performance or not, versus this observational thing of I'm seeing that this slice has low performance, but is this really why the model, is the way I constructed the slice the reason why the model is worse on this slice, right? So those are kind of two different things. And so you might see a slice where the pause tag is maybe all sentences that contain NPZ or whatever, right? Something like that. And you might construct that slice, but really the reason it's bad is because it contained a bunch of data that came from a different source, right? Something like that. So that's what's hard to tease apart, I think, with the general slicing functions that one might write. And so, yeah, I think I'm still not super clear. To be honest, I can't give you a very good answer to your question, but I think for a lot of domains, domain specific problems, like let's say text summarization, which is, fairly broad still, but still a specific task, you can construct slices that are interesting, I would say, like things like, head bias, most summaries tend to summarize the first 3 sentences and so on. So things like that. So there's definitely, scoping that you can do in terms of the pyramid.
Yeah, cool. Yeah, thanks.
I also had an additional question on the Mandoline work. Could you speak a little bit at a high level about the trade-offs when, first of all, it's extremely cool, right? That by defining some slicing functions, you can evaluate or estimate performance without on kind of especially important subsets without having labeled data. That's really cool. Is there are there settings when it works particularly well versus some that it struggles in, and how do you think about those trade-offs?
Yeah, I think the key in Mandoline is being able to define slices properly. And so one of the reasons why I was excited about using Mandoline as part of Snorkel Flow is because the slices that you want inside Mandoline are the ones that the model is using particularly in its prediction. So it's kind of slices that are not irrelevant slices. They're relevant to the model and relevant to the task. And so specifically when you consider, how you build models with labeling functions, you're actually giving pretty clear signal, especially if you take like the actual label model as the predictor. What you have is essentially a model that uses some of these signals. And so you can use those labeling functions as part of the slices as well. And that I think is one setting in which it might do particularly well. I think the settings where it doesn't do well is where you throw in 500 slices or 200 or 100 or even 50 slices, and a lot of them are not relevant. So you can imagine an irrelevant slice. Let's say the presence of the word, the presence of like uppercase text, right, in your corpus, and then maybe all your text in deployment data is lowercase, right? But maybe your model is actually using internally a preprocessor that lowercase is all the text, so it doesn't actually know the difference. But you might be really kind of thinking, oh, like I had like 50-50 uppercase, lowercase in my validation. Now I have 0% uppercase. So maybe my model is really going to be bad now because that data has shifted a lot. But there's actually no distribution shift that you should care about here because your model actually doesn't even use that information. So that's where you have to be really careful about what features are you seeing that are shifting, but they're actually not very relevant to your model's prediction. And so if you have a lot of those, then the performance of Mandoline is really bad. But if you don't, then it's really good. And in the paper, we actually had some hacks to like construct these pretty task agnostic slices that work, I would say, pretty well across most of the tasks that I've seen. So there are ways around that, basically.
Awesome. That's helpful. Thank you. All right. Anyone else with a last burning question for Karan? Cool.
Okay, great.
Well, why don't we wrap here? Karan's around, at least for the snorkelers. We can keep bothering him on Slack and schedule some follow-ups. But thank you everyone for showing up today, both snorkelers and our public guests. And thank you, Karan, for an amazing summary of your work. This is a really exciting area and obviously super relevant to the system we're building here at Snorkel. So thanks again.
Thanks for having me. Yeah, really, really fun. Thanks.
All right. Thanks, everyone. Bye.
Bye.